Hello everyone. The purpose of this example is to demonstrate different ways to schedule a multi-product microbial biopharmaceutical facility using SchedulePro, and how to use the outputs of the program to analyze and update the schedule. This example is intended for individuals who are in charge of planning and scheduling of manufacturing activities for multi-product facilities. Engineers involved in the design and debottlenecking of such facilities will find the material of value as well. Although the processes modeled in this example are microbial biopharmaceutical processes, the concepts explained in this video are not limited to biopharmaceutical processes. They are applicable to any batch multi-product facility. Before viewing this video, please make sure you watch the Fundamentals of SchedulePro series of videos under the training page of our website. These 3 tutorial videos explain the basics of creating a project in SchedulePro, including information on how to create facilities and equipment, define recipes, assign resources, create campaigns, etc. Those concepts will not be repeated here. You may also view the SchedulePro overview video, which provides a summary of SchedulePro's capabilities. Furthermore, please note that the files that will be discussed during this video are part of the microbial bioprocessing example that is shipped with SchedulePro. There is also a README file in PDF format associated with this example, which explains the example in greater detail. This can be downloaded from the link shown here. Please download this README file for additional information on this process and the files associated with it. Additional information related to the creation and analysis of projects in SchedulePro is also available in the SchedulePro manual, which can be downloaded from this same web page. In particular, the Chapter 4 tutorial in the manual has detailed information on flexible shifts, changeover times, equipment routing, facility downtimes, and much more. Let's take a look at the microbial production example now. In this tutorial, I will first describe the plant and its associated equipment, as well as a basic microbial process that we will be modeling. Next, I will describe how to add flexibility to the recipe, so that operations may be automatically shifted in order to avoid conflicts related to equipment or resource availability. I will also show the scheduling results for the basic microbial process. Then I will provide a simple throughput analysis and debottlenecking example where a second equipment line is added to the upstream portion of the process in order to double the throughput of the plant while adding minimal equipment. Case B will expand upon Case A by modeling 2 similar products running within the same multi-product plant. Initially, both products will use the same equipment line for all operations. Then the process will be modified so that 2 different equipment lines are used for the 2 recipes, although a few equipment items will be shared by both processes. Case C will add buffer preparation and holding activities to the recipes. In the first part of this case, the prepared buffers will be completely consumed during every single batch. Then the example will be modified so that a single batch of buffer material may be used for multiple production batches. In this case, additional batches of buffer will be automatically scheduled whenever necessary, based on the inventory level of a storage unit. The example will then be modified again in order to show the use of mobile storage units and to account for their floor space requirements. Case D will show how to visualize the instantaneous and time-averaged requirements for a resource such as purified water. It will also show how cascaded material supply systems may be used to track production of a material that is later consumed to produce another material. Then a weekly outage will be added to the material supply system to account for loop sanitization, and the impact on the schedule will be analyzed. The final case, E1, briefly describes SchedulePro's use of equipment changeover matrices to automatically account for cleaning which may be required if certain equipment sits idle for an extended period of time. This will conclude this example. This series of cases has been broken into several videos. Video 1 will describe the basic microbial process and demonstrate the Case A files. Video 2 will demonstrate cases B and C. Finally, Video 3 will demonstrate cases D and E. Returning to the process description, this diagram is a simplified representation of a microbial biopharmaceutical production process. The process is broken into two sections: the upstream section, in black, where the product is produced, and the downstream section, in blue, where the product is purified. To keep things easy to understand, only the main process stream is shown flowing from one unit to the next. All other material input and output streams are excluded from this diagram. In addition, to keep this example simple, certain processing steps, such as inoculum preparation, inline filtrations, buffer preparation, etc., are excluded. As you can see, the basic process begins with a small-scale seed fermenter, which feeds the main production fermenter. The fermentation broth is then sent to a harvest tank, which feeds a centrifuge. The product stream from the centrifuge flows to the CF pool tank. The material in the CF pool tank is then fed into an ion exchange chromatography column. The column eluent stream, which contains the partially purified product, is then sent to the ion exchange pool tank, which is used to feed the hydrophobic interaction chromatography column. The product stream from this column is pumped to an ultrafiltration diafiltration unit, where it is further purified. Finally, the purified product is freeze-dried. Each of the unit procedures in the previous slide contains one or more operations. For example, the operations associated with the first two unit procedures, the seed fermentation and main fermentation, are shown on this slide. Each of these operations was given a descriptive name, a duration, and relevant scheduling links when the SchedulePro file was constructed. The fundamentals of recipe creation, including specification of unit procedures and operations, are explained in a series of video tutorials within the training section of the IntelliGen website, as described previously. Therefore, the steps required to create recipes will not be repeated here. Switching to the SchedulePro interface, we can see the recipe that has been defined for this example under the Recipe node of the Explorer tree. We can visualize this recipe in the form of a Gantt chart by selecting the recipe in the Explorer tree and clicking this button. The procedures within this recipe, seed fermentation, etc., are displayed with dark blue bars. The operations within each of these procedures are represented by the light blue bars. The duration, start time, and end time of the various activities are also displayed in the corresponding columns of the table on the left. The recipe Gantt chart provides a quick and easy way to check the process model to ensure that the scheduling of operations within a batch is specified correctly. You can also get a clear understanding of the flow of a given recipe by viewing the recipe block diagram. Each rectangle in the recipe block diagram represents a procedure. The blue arrows that connect the various operations of the procedures indicate scheduling links among those operations. If the recipe includes information on consumption and generation of materials, Those will be indicated by black horizontal arrows linked to operations. The recipe Gantt chart and block diagram facilitate editing in addition to visualization of a batch process. For instance, double-clicking on an operation in the recipe block diagram will bring up that operation's properties dialog. Here, changes to the recipe's current specifications, including operation durations, scheduling links, etc., can be made. Note that if campaigns of this recipe are already scheduled on the production schedule, those campaigns should be unscheduled before modifications are made to the recipe. The campaigns would then be rescheduled after the modifications are complete. To learn more about recipe creation, initialization and editing of operations, and scheduling of campaigns, please refer to the training videos mentioned a few minutes ago, as well as the SchedulePro manual mentioned at the beginning of this video. After the recipe specifications are reviewed and the campaign has been scheduled, the results can be viewed in the form of an Equipment Occupancy Chart, or EOC. The horizontal axis of this chart shows the timeline, while the vertical axis shows the equipment that is required. The colored bars on the chart indicate when operations occur in each equipment item. Notice that there are gray bars on this EOC as well, which represent facility downtime for the downstream process. In this case, there are 2 8-hour shifts per day in the downstream purification section, with no labor resources available from midnight until 8 a.m. As a result, certain activities can only be performed during the period from 8 a.m. until midnight. This is why certain procedures in the EOC have breaks between operations. Since there is no labor available to these procedures during the night shift, the start of subsequent operations must be delayed until the morning. These delays were automatically performed by SchedulePro based on flexible shifts that were assigned to relevant operations of the Product A recipe. Note that it is also possible to allow operations to run during plant downtimes if desired. For instance, the freeze-drying operation in lyophilizer LYO1 may continue during plant downtime as long as the operation is commenced during normal working hours. This is why the operation bars for LYO1 continue through the gray facility downtime. Flexible shifts and specifications related to activity during plant downtime are defined at the operation level. For instance, here you can see that the freeze-dry operation has a flexible shift associated with it, as indicated by this checkmark. The flexible shift was assigned on the Scheduling tab for this operation. As you can see, there are 3 different options for the start time reference of an operation. In this case, we have chosen to start this freeze-dry operation at the end of the previous operation. However, it is also possible to specify fixed or flexible time shifts relative to the reference operation, as you can see here. A positive shift is a delay with respect to the scheduling link, whereas a negative shift is a lead time. In other words, if there is an operation with a start-to-start specification and a fixed shift of -5 hours, that operation will start exactly 5 hours before the reference operation starts. In contrast, a flexible shift specifies a maximum shift that may be applied by SchedulePro in order to avoid over-allocating resources associated with the operation, such as labor, raw materials, auxiliary equipment, etc. Flexible shifts are typically assigned to operations in which delays will not adversely affect the product or process. In this case, the 72-hour flexible shift assigned here allows the freeze-dry operation to begin up to 72 hours after the transfer from UF-DF operation is completed. Adding flexible shifts to the recipe allows SchedulePro to automatically move operations when conflicts arise in order to meet equipment and resource constraints. Note that when a flexible shift is specified, it is also necessary to specify which criteria to use when determining whether the shift can take place. For example, shift for facility closure, equipment availability, etc. Notice that the Scheduling tab also allows an operation to be interrupted up to a certain maximum time and up to a certain number of breaks. This permits an operation to be stopped and then later restarted. For instance, let's assume that a 4-hour operation can only be performed during the day shift because that section of the plant is only open during the daytime. If that operation is started 3 hours prior to the end of the day shift, it will not have enough time to be completed prior to the end of the shift. However, the operation could be stopped at the end of the shift and then restarted the next morning. At that point, it would run for the remaining 1 hour and then be complete. As was mentioned previously, it is also possible to allow certain operations to run during plant downtimes. This is specified at the bottom of the Scheduling tab. For additional details related to specifying recipe flexibility, please refer to the SchedulePro manual. Switching to another example, let's consider how to improve the weekly throughput of a plant. In this case, the facility downtime that was shown on the previous EOC has been removed. As a result, all equipment is available for use at all times. As before, the results for this production schedule can be viewed on the EOC. The EOC for this file shows a 6-batch campaign with a 72-hour cycle time between consecutive batch starts. This results in a modest break between consecutive batches in the production fermenter. This slack time between batches is desirable in order to accommodate processing variability and delays. However, notice that most of the equipment in this plant is idle most of the time. To improve the plant's productivity, we can add another upstream equipment line, i.e., an extra seed fermenter and production fermenter. This will eliminate the current cycle time bottleneck. This strategy is shown in case A4. Here you can see that an extra production fermenter has been added to the plant. This change allows FR1 to be used for the fermentation in the first batch, FR2 to be used for the fermentation in the second batch, FR1 to be used again for the fermentation in the third batch, etc. By switching back and forth between two fermenter trains, the batch cycle time can be reduced from 72 hours to 36 hours, which means that a new batch is started every 1.5 days. Therefore, the addition of the second fermentation train doubles the production capacity of the plant, while only modestly increasing the total capital cost of the facility. To assign the additional fermenter, the recipe was selected in the Explorer tree, the fermentation procedure was selected in the pane on the right, and the Edit Procedure button was clicked. Next, the Main Equipment Pool tab was selected, and FR2 was added to the equipment pool. Note that each entry within an equipment pool represents an alternative equipment unit that can be used by the procedure. In each batch, only one of the equipment units will be assigned. The order in which the equipment appears in the list is the priority in which they will be assigned, assuming all equipment units are available. The prioritization may be changed with the Move Up, Move Down buttons immediately above the list. This same process was followed to add the extra seed fermenter to the seed fermentation procedure. This concludes part 1 of this tutorial example. Please join me for part 2 of this example, where I will explain how to model multiple products running within the same plant, and explain how to incorporate buffer preparation and holding activities into the recipe.